Good morning, good afternoon, good evening, class. This is Mr. Arocena, and on today's video, we'll be talking about how to deal with mixtures of strong acids and bases. We'll deal with mixtures of weak acids and weak bases at another time. They're a little more difficult because of their equilibriums. So we'll talk about the easier to work with strong acids and bases today first. Alright, so from last lesson we talked about the pH scale and the pOH scale by extension. I just want to show you guys this relationship of how the two should be viewed. So here we have on the one side, so the top side, we have the pOH, and on the bottom side we have the pH. Now if you remember from the last video, pH plus pOH should equal 14, and you can sort of see that relationship here. So like, for example, if I have a pOH of 13, I have a pH of 1. If I have a pOH of 2, I have a pH of 12. So this is going to be kind of our guiding principle when we talk about how acidic or how basic something is. Okay, now the neutral pH will be the one right in the middle, so in this case this would be our neutral pH. And if you notice that neutral pOH is the same. Okay. You should also notice that if the pH, so here's the pH, if the pH gets smaller, the pOH gets larger. Whoops. Now this means that as something gets more acidic, so remember this side is more acidic, low pH is more acidic, then the substance becomes less basic. And similarly, a low pOH means that it is going to be more basic and less acidic. So again, in a similar fashion to the pH, how a low pH is more acidic, a low pOH is more basic. High pH is less acidic, high pOH is less basic. All right, there you go. So it's kind of like a neat relationship, quick review of what we talked about in the last video. Now, when you mix strong acids and strong bases together, one of three things will happen. Okay, so the resulting mixture will either become acidic in nature, it'll become basic, or it'll become neutral. And how we figure this out is quite simply, we just determine how much of each reactant is present. And when they mix together, they will undergo their acid-base neutralization, and you'll end up with either more moles of acid, or you'll end up with more moles of base. And it just basically falls to us to calculate, what do we have more of? Do we have more moles of acid or more moles of base? Because if you recall, our generic acid-base reaction will be as follows. Acid plus base will produce H2O and a salt. And depending on the balanced equation, we just have to calculate, okay, do we have enough acid to react all the base? If we do we have any leftover acid? Or similarly, do we have enough base to react with all of the acid? And then if we do we have any leftover base? So what follows then will just be a bunch of examples of how to do this. And really this is just a lot of stoichiometry, a lot of chemical stoichiometry. So it shouldn't be too bad, and this should be a review of stoichiometry from like Chem 11 with a specific sort of focus on acid-base reactions. So here's the first example. What is the pH of a mixture of 10 milliliters of 0.1 molar HCl and 90 milliliters of 0.1 molar NaOH? Okay, now intuitively I think you guys can kind of know what's going to happen, because if here's the acid and the base are at the same concentration, which do we have more of? Okay, well, we only have 10 milliliters of HCl, where we have 90 milliliters of NaOH. So we should immediately suspect that this particular mixture should be basic in nature. So final result should be basic. Okay, final result should be basic. So this is kind of our initial look at this question. And if our calculations show otherwise, we probably did something wrong in our calculations, because it doesn't make any sense to have, if our acid and base are the same concentration, I have more base. So if my solution ends up becoming acidic, that doesn't make any sense. Anyways, let's get started on how we should work this out. First things first, we need a balanced chemical equation. So here's where chemistry 10 will come into play, where we'll have to write out the acid-base neutralization reaction. Okay, now this is just going to be a single replacement, HOH plus NaCl. There we go. All right, now we don't actually care about the product side of this because the products don't matter. We just know it's going to neutralize. What we really want to know is how are the acid and base related. In this case, it's a 1-to-1 ratio, and to be fair, almost all strong base, strong acid reactions will be 1-to-1. So these problems are actually quite easier than the stoichiometry problems we did in Chem 11. All right, so we have a 1-to-1 ratio of hydrochloric acid to NaOH. So basically it means if I have 1 mole, for every mole of hydrochloric acid, I will react with 1 mole of NaOH. All we need to do now is figure out, well, how many moles of HCl do we have? And how many moles of NaOH do we have? Okay. To do this, we can simply calculate it as follows. We have the concentration and we have the volume here. So from our molarity equation, let me right over here. Molarity is moles per liter, or moles per volume. So moles will be molarity times volume. All right. So here I will do the following then. So the moles of HCl will be its molarity, 0.1 molar, times its volume. I'm going to leave it in milliliters. Okay, and this will give me an answer of 1.0, and this will be in a unit of millimoles. Okay, so I'm going to leave the milliliters as milliliters, and then my final answer will be in millimoles. We can do the same calculation for the NaOH. So our NaOH is, again, same concentration, but we now have 90 milliliters of NaOH, and this will give us an answer of 9 millimoles. All right, so now, which one do we have more of? Do we have more NaOH? Do we have more moles of NaOH, or do we have more moles of HCl? Well, we have more moles of NaOH, so this solution should be basic. And how basic is it going to be? Well, we can quite simply just do the following calculation to determine how basic this solution will be. So we just calculate leftover moles of NaOH. Because based on our balanced chemical equation we wrote here, every 1 mole of HCl will react with 1 mole of NaOH. So we can take our moles of NaOH and we can subtract from it the number of moles of HCl that will react. So altogether, we are left with 8 millimoles of NaOH. There you go. I'm going to need a little bit more room, so let's give me a minute. All right, so here we are. So our final answer from, or not final answer, our answer from the previous thing was we had 8 millimoles of NaOH. This is how many moles of NaOH we have left over. This is our base. Now, because it's a strong acid, oh, sorry, not strong acid, because this is a strong base, the 8 millimoles of NaOH will dissolve to create an equivalent amount of OH ions. Okay, and this is what makes strong acids and bases really handy to work with, because there's a leveling effect. So we'll call this leveling effect. The NaOH will create an equivalent amount of OH minus. All right, now we have the amount. Now we have the moles of OH minus. We're still asked to find the pH. Now we cannot find the pH from the OH minus. However, we can find the pOH. Find pOH. And we can use our formula from a previous lesson where pOH is the negative log of the concentration of hydroxide ions. So all we need to do now is find the concentration of hydroxide ions. Now the concentration of hydroxide we can calculate as moles, or in this case millimoles per milliliter. So we have our 8 millimoles of hydroxide. Now because we are mixing these, the total number of milliliters will actually be the 10 milliliters plus the 90 milliliters. Okay, so keep this in mind. Because we're mixing these two things together, the actual volume does change. So this will be 8 millimoles over 100 milliliters to give us a total concentration of 0.08 molarity. So now that we have the concentration of hydroxide, we can take this, throw it into here, and then we can calculate the pOH as negative log of 0.08. All right, so this should actually be something around like 2 or 3. Yeah, I think around 2 or 3. So 0.08. We'll take the logarithm of that. Oh, that's way off. It's actually 1. So that's negative of negative 1. So it's about 1.1. Because my pOH is about 1.1. Actually, that's about right, because 0.8 is very close to 0, or 0.08 is very close to 0.1. So it's approximately 0.1, and the logarithm of 0.1 is negative 1. So the negative log of that would be 1. So this is good. This is good. All right. So now we have the pOH. pH, if you remember, pH will be 14 minus pOH. So it's going to be 14 minus 1.1 for a total pH of 12.9. There you go. Final answer, 12.9. Which again, doesn't contradict what we originally thought about the solution, because we thought that based on our reading of the problem, the final solution should be basic. We did the calculations to show that we did have a lot of excess hydroxide, so it should be a basic pH. Doing all the calculations, we got our pOH, which is really basic, and then translates again to a pH, which is also quite basic. So our math is correct. It matches up with our intuition of having a lot of excess sodium hydroxide, so it should be quite basic. All right, let's go do another example. So in this example, it's asking us how many moles of HCl must we add to this many mole, or this substance, so this solution, 40 milliliters of 0.18 molar NaOH to produce a pH of 12.5. And we're going to assume no change in volume. Otherwise, we'd have to change some of the calculations. So we're going to stick with a volume of this. And we're going to pretend the volume doesn't change as we add moles of HCl to this. All right, so first things first, we want to figure out, what can we figure out first? We have pH of 12.5, 12.5. And from here, we should be able to determine the concentration of hydronium. Because the concentration of hydronium is 10 to the negative 12.5. Okay, so remember, concentration of hydronium is, I've written it out here. Concentration of hydronium is 10 to the negative pH. Okay, so this will allow us to calculate what the concentration of hydronium is. Let's quickly do that. 12.5 negative 10 to that power. So 3.16 times 10 to the negative 13. 3.16 times 10 to the negative 13. So that's our goal, is to have a total concentration of hydronium equivalent to this. Okay. All right. From the NaOH, we can actually figure out from the NaOH, we can figure out the amount of hydroxide. So the concentration of hydroxide will be, again, because of the leveling effect, the concentration of hydroxide will be the same. And then from here, we can actually figure out what the pOH is of this solution. So the pOH will be negative log of the concentration of 0.18, which is going to be, let's find out, logarithm, so it'll be negative 0.7, we'll make that negative, so 0.7, and I'll take two significant figures, so 0.74. That's my pOH. Yeah, that's my pOH. So the original, this is our original pOH. Original pOH. And then from here, we can calculate the original pH. So therefore, our original pH is going to be 14 minus that. So 14 minus 0.74 to give 13.26. Okay. This will tell us kind of how many, what the concentration of hydronium is currently present and what we need to add to it to make it bigger. Yeah, so from here we can calculate the original amount of hydronium, original concentration of hydronium as 10 to the negative pH, 10 to the negative 13.26. 13.26 negative 10 to the, whoops, no, that's right. So the original concentration is 5.5 times 10 to the negative 14. 5.5 times 10 to the negative 14. And then from that concentration, we can calculate the original moles. Call this original moles of hydronium, H plus as the concentration, let's make concentration 5.5 times 10 to the negative 14 molar, and then times the volume, in this case 40 milliliters. So we have a ridiculously small number of moles, so 2.2 times 10 to the negative 12 millimoles. So this is our original original amount of moles of hydronium. All right, now going back to the beginning, the very first value we calculated up here. So this value here, this is the concentration of hydronium we want to get to. So now we'll do a similar set of calculations for what we want. Okay, so we want a concentration of hydronium of, what's that, 3.16? 3.16. 3.16 times 10 to the negative 3 molar. So the moles then of hydronium in this case will be 3.16 times 10 to the negative 3 molar. We're not changing the volume, so we can leave it as 40 milliliters. And then this will give us, oh, it should be 13, not 3. Now we do the calculation, so 3.16 times negative 13 to the 10. That's a really small number. And times the 40 milliliters. So 1.26 times 10 to the negative 11. That's how many millimoles we have. 1.26 times 10 to the negative 11 millimoles. So here's how many millimoles we want to get to. Here's how this number here is the millimoles we currently have. So we need to add altogether 1.26 times 10 to the negative 11, subtract the amount we currently have, 2.2 times 10 to the negative 12, and this will give us an answer of something still really, really tiny. So there's my 1.26. We'll subtract from that 2.2 times negative 12 to the 10. So we need to add 1.04 times 10 to the negative 11. 1.04 times 10 to the negative 11 millimoles of hydronium. And the question was asking us how many moles of HCl. So because of leveling effect, we add 1.04 times 10 to the negative 11 millimoles of HCl. And that will change the pH value to the value that we want. That's a very, very small number. So we'd either use a very, very low concentration hydrochloric acid, or we would just use a very, very small amount of a higher concentration hydrochloric acid. There you go. So much like the previous example, we're just kind of comparing moles, and then we just kind of kept using our pH calculations, pH equations to go back and forth from one number to another. All right, let's go through another example. So this example asking us what is the pH that results when we mix these two solutions together. This one's interesting because we're using calcium hydroxide, and it's an interesting strong base because it's not like sulfuric acid, which was a really interesting strong acid. So here, the calcium hydroxide, this will actually do something different than what we would have expected. It's kind of an exception, similar to how sulfuric acid is kind of an exception to what we would expect of strong acids. So calcium hydroxide does the following. It's got two OHs, so it will actually dissolve into this. Okay, and then because we need to balance everything properly, you actually end up getting a ratio that's not 1-to-1. So calcium hydroxide doesn't generate an equivalent amount of hydroxide. It actually generates twice the amount of hydroxide. So this is kind of an interesting exception to our leveling effect. Okay. And what does this mean for our calculations? Well, it just means then that for every one mole of calcium hydroxide actually requires 2 moles of nitric acid. But the process is still the same. We still have to calculate how many moles of hydroxide do we get from the calcium hydroxide. Okay. And then, well, that's one way to do it. If you do it moles of calcium hydroxide, we actually could do that. Let's do it moles of calcium hydroxide. And then moles of nitric acid. And we just have to understand that we actually have a 2-to-1 relationship between the calcium hydroxide and nitric acid, or sorry, 1-to-2 relationship. So let's say, okay, my calcium hydroxide, to calculate this, we will take our concentration of calcium hydroxide, which is 0.1 molar. We'll multiply this by the volume, so 15.0 milliliters, to get an answer of 1.5 millimoles. The nitric acid, we have a concentration of 0.2 molar. We still have the same 15 milliliters. So we have, in this case, we have, slightly more. We have 3.0 millimoles of nitric acid. So in this situation, we need twice as much nitric acid to neutralize the calcium hydroxide. Looking at our numbers, we have 1.5 millimoles of calcium hydroxide. We have 3.0 millimoles of nitric acid. So our, I guess our end result is we actually have enough of everything. Now, some people are like, well, is that true? Let's expand this problem a little bit. All right, so we're going to expand this problem a little bit because it might not be super clear. We have 1.5 millimoles of calcium hydroxide. Okay, and then we have 3.0 millimoles of nitric acid. Now, because the calcium hydroxide will create twice as many hydroxide ions as itself, because it's got 2 of them, this will actually create 3.0 millimoles of hydroxide. Now, the nitric acid being a strong acid, because of leveling effect, this will create 3.0 millimoles of hydronium. Okay. Now, when you look at these numbers, do we have excess of either this or this? No, we don't actually. We have equal amounts of hydroxide, and we have, as we do of the hydronium. So end result is we have no excess hydroxide, we have no excess hydronium. So what is this solution going to be? Is it going to be acidic? Nope, because we don't have excess hydronium. It's going to be basic? Nope, because we have no excess hydroxide. So this solution is therefore neutral. And what is the pH of a neutral solution? At room temperature, the pH would be 7. It's a common thing that a lot of students forget, is that neutral solutions do have a pH value. It's 7. There we go. All right, so if you have your textbooks, then your assignment will be as follows. Okay, there's going to be a lot more calculations. If any of you have any questions about the exercises, if the solutions don't make any sense and you want me to go over them, do let me know. You guys all know how to contact me.